Following up on our discussion about determining the empirical formula from mass, now I would like to look at that same type of problem, but from percent composition. Percent composition is information that we might actually get back from an elemental analysis rather than a mass for a specific compound sample that we sent. And really what it's going to do is it's going to tell us what percent of the overall compound is a specific element. So to calculate percent mass from a compound, if we knew its chemical formula, we would really just need to know the molar mass of the overall compound and the mass, the atomic mass of the individual elements. So let's look at an example of that using carbon dioxide. So we have CO2. So to understand what the percent of carbon is going to be, we would take the mass of carbon, and this is going to come from my periodic table. So it's at 12.01 atomic mass units. So we're thinking about it as one carbon atom within one carbon dioxide molecule. But you could apply this to a mole as well. And then we're going to divide that by the mass of the compound. And so this is that molecular mass for the entire compound. And so for carbon dioxide, it's 44.01 about. And so we'll divide that 12.01 by the molecular mass of the entire compound, 44, and multiply it by 100. Be careful with your calculator if it has a percent button. Some of those percent buttons actually would give you an answer that's 2 digits off. Really, we're multiplying it by 100 to give a percentage. And so in this case, we're going to end up with 27.3%. For our oxygen, we have a mass of oxygen that is 15.999. And we know that we have 2 oxygens in our compound. And so we're going to incorporate that mole ratio between our oxygen and our carbon. And so we've got 2, we have 2 right here on front of our 15.99 that is coming from that 2 subscript after the oxygen. So we'll multiply these together and divide it by 44, which is again that molar mass that's coming from the periodic table. And we'll get a value that is 72.7%. And so these are our percent compositions for our individual elements within the molecule carbon dioxide. So here's how we can use that to determine empirical formula. So here I'm given a compound's percent compositions. I've got 2.1% hydrogen, 32.7% sulfur, and 65.2% oxygen. And I need to figure out what the empirical formula is. Now, I've already talked about a strategy for taking mass and getting to our empirical formula for each of our elements, but these are percentages. So I have to make an assumption, and that assumption is going to be a mass of my compound, and it can be any mass I want. Because I have the percentages of each of my elements, I can take any sample size and get the same ratio of my hydrogen to sulfur to oxygen by using my percentages, right? So I can make it 3 grams. I can make it 27 milligrams. It doesn't really matter. The easiest one to do is to assume 100 grams. So I'm going to assume I have 100 grams of the compound. All right, so if I have 100 grams, I know that 2.1% of 100 grams is equal to the amount of hydrogen in the compound. So really what that is it's 100 grams times my 2.1%, which remember is 2.1 divided by 100 when I'm actually using this in a multiplication operation, or 0.021. That means that it's going to be 2.1 grams. And this is why I chose 100 grams to start with. It means that I can take that 2.1% of hydrogen and say, oh, well, I've got 2.1 grams of my total 100 grams. And so that means that for my sulfur, I'm going to have 32.7 grams of sulfur, and I'll have 65.2 grams of oxygen to start with. And now I have ended up at the starting point of my previous example where I determined empirical formula for masses. I have masses now. Now I just need to follow my 3 steps, which are 1, convert to moles, 2, simplify the mole ratio, and 3, write out my empirical formula. So let's do that. So I've got my 2.1 grams of hydrogen. I'm going to convert that into moles by multiplying by 1 mole and dividing by the molar mass in grams. And so that is going to be 1.008 grams. And that's just coming off my periodic table. And when I do that, I get a value that is 2.0833 moles. And I'm really looking at 2 significant figures here, but I'm going to keep all my digits for now and just underline my sig fig. I'm going to probably be rounding to 1 anyway, right? So it won't matter as much here, but I'll do it for the practice. So sulfur, I've got 32.7 grams, and now I need to convert into moles. This is equivalent to just dividing by the molar mass. So I'm going to use my 1 mole of sulfur is going to be equal to 32.065 grams, and that's just straight from the periodic table. And when I divide 32.7 by 32.065, I get 1.0198 moles of sulfur. I'm sorry, 3 sig figs. And now I have oxygen. So my oxygen molar mass is, for every 1 mole, oxygen weighs 15.999 grams. And that's going to give me a value of 4.0753 moles of oxygen. So now I'm going to compare that 2.0833, 1.0198, and 4.075, and I'm going to identify that 1.098 as the smallest. So I'm going to divide each number by that. So I'm going to divide this by 1.0198. I'll divide this by 1.0198. And I'll divide my oxygen moles by 1.0198. And what this is going to give me when I do that is about the same number, right? And so I'm going to round, and I'm going to find that I get to an empirical formula that has 2 hydrogen, 1 sulfur, and 4 oxygen, H2SO4, or sulfuric acid.